Hi, everyone. I'm Z from Tongji University. Now I'm delighted to present our latest work in CVPR 2023. NeuralPCI, Spatio-temporal neural field for 3D point cloud multi-frame nonlinear interpolation. In this paper, we propose a novel method for point cloud interpolation called NeuralPCI. Given a point cloud sequence, the target of NeuralPCI is to interpolate a few frames of point cloud between every 2 frames in the sequence. As a result, we can convert the sequence with a low frame rate into one with a higher frame rate. Before delving into the details, let's take a brief look at the result. In contrast to the original input sequence of point clouds, NeuralPCI can output a smoother and more fluent sequence at a high frame rate. Now let's return to the background of point cloud interpolation. Due to hardware limitations, the 3D scanner or lidar has a relatively low frame rate. Therefore, the interpolation algorithm is necessary and valuable. However, the irregular and unordered structure of point clouds makes it hard to find correspondences between frames, and we cannot average or interpolate points directly. Furthermore, a large amount of nonlinear complex motion exists in real-world scenarios, such as dynamic motions of humans and vehicles. The results of uniform interpolation differ significantly from the actual situation, so nonlinear interpolation is the key. Here are more examples of nonlinear motions in outdoor scenes. And we also construct the NL Drive dataset from public autonomous driving datasets to support interpolation experiments. In fact, video frame interpolation has been thoroughly investigated in the image field. Common methods rely on optical flow estimation to produce the intermediate image frame. Similarly, previous SOTA point cloud interpolation methods combined the bilateral scene flow to generate the interpolated frame. However, they only take a pair of point cloud frames as input, which is not enough to estimate the nonlinear motion. Inspired by NeurF, we construct a 4D spatio-temporal neural field that receives multiple point cloud frames as input to extensively exploit multi-frame information. Consequently, we propose NeuralPCI, which is a multi-frame point cloud interpolation algorithm to deal with both indoor and outdoor scenarios. It integrates motion information implicitly over space and time and outputs point cloud frames at an arbitrary given time. Moreover, NeuralPCI is a flexible and unified framework for interpolation and extrapolation. Following is an overview of the NeuralPCI architecture. Firstly, we establish the mapping from the coordinate field to the motion field through the coordinate-based MLP, and use interpolation time as an independent input to control the prediction. Then, we feed the spatial and temporal coordinates of input frames into NeuralPCI, and adjust the interpolation time for each input timestamp to generate the corresponding point cloud. In such a way, we can calculate the loss between the input and predicted point clouds. Each input frame itself serves as a constraint for optimization, allowing for a more elegant way to incorporate information from multiple point cloud frames. For the self-supervised losses, we use chamfer distance loss as the main term, which calculates the nearest neighbor distance between points. In addition, we introduce the earth mover's distance loss for better density preservation and smoothness loss for local rigid motion consistency. Similar to NeurF, NeuralPCI optimizes each new sample from scratch during runtime. The graph of the curve demonstrates that NeuralPCI has excellent convergence. After self-supervised optimization, the network's weight is frozen for inference. Given the reference point cloud and interpolation time, NeuralPCI could generate the corresponding interpolation frame. Finally, we conducted the interpolation experiments on both indoor and outdoor datasets. As shown in the tables, NeuralPCI outperforms previous SOTA methods, indicating excellent performance in a variety of situations. Here are the comparison results, which clearly demonstrates the effectiveness of NeuralPCI and that it can preserve more local details than other methods. The same holds true for outdoor scenes, where the interpolation frames generated by NeuralPCI are closest to the ground truth. Beyond the interpolation task, NeuralPCI can also be applied to many other fields. For instance, we can input the keyframe with labels into NeuralPCI to obtain the interpolation frame, which inherits the labels, and then assign the label via KNN to the realistic point cloud frame for auto-labeling. Besides, it is possible to interpolate point clouds of different shapes to construct the process of point cloud morphing. In conclusion, NeuralPCI extends input from pair frame to multi-frame, thereby expanding the receptive field of the time domain and enhancing nonlinear interpolation capabilities. The essence of NeuralPCI to generate interpolation frames comes from the excellent fitting ability and smoothness of MLP. And the self-supervised optimization prevents NeuralPCI from the out-of-distribution problem of learning-based methods. From a unified perspective, we could utilize the neural field as a powerful tool to bridge different tasks. Indeed, NeuralPCI also has some limitations. The per-scene runtime optimization limits the real-time application. And there is still improvement space for large scenes and extrapolation, which remains a future work. Thank you for listening, and welcome to our project page for more details.